Okay, let's recall the definition of Laplace transform. So the L of your function f, some function, equals integral from 0 to infinity your f of t times e to the minus st dt. Okay, so theorem 15, we have to show the Laplace transform of sine of kt equals k over s squared plus k squared, and 2, the Laplace transform of cosine of kt equals s over s squared plus k squared. Okay, so let's write the definition of Laplace transform of sine right here first. Okay, so here's my Laplace transform of sine. So I'm putting sine of kt in place of f up here. So it'll be sine kt e to the minus st integral 0 to infinity. And notice here I'm leaving off the s on these guys just for ease of notation, but it should be an s there, but I'm just leaving it off because I want to keep writing s. Okay, so we have to integrate this guy now. This is going to require integration of parts since we're multiplying two functions here. So let's recall integration of parts down here. Okay, so we're going to find the indefinite integral of this guy first. I'll worry about the limits later. So here's my integration of parts formula. So whenever you have a sine or cosine and an e, you want to let the u equal the sine or cosine and the dv be the e term, which I've done here. So I'm going to let u be this, dv be this. So let's work those out over here. So doing that, we get, so my u is sine of kt. So taking derivative on both sides with respect to t, derivative of sines, cosine, and derivative of kt with respect to t would be k. So it'll be k in front here. So it's going to be k cosine kt. Then multiplying both sides by dt. We'll have our du equals k cosine kt dt. Okay, let's work on the dv next. Okay. Okay, so first recall that if you integrate e to the kt with respect to t, it's going to be e to the kt over k, I guess plus a constant. Don't worry about the constant here. So then if my dv is this guy here, my v then will be integral of dv. So it'll be integral of e to the minus st dt. So the k here would be minus s. We're going to be e to the minus st over minus s. Okay, let's keep going. Actually, just notice something here. I should have used a instead of k here because we have k as defined as something different up here. So let me just call this a, where a can be anything at all. So therefore it'll be this. Okay, now let's substitute into the integration of parts then. So in place of u, we'll have our sine kt. In place of v, we'll have our e to the minus st over negative s. In place of du, we'll have this. So replacing here, we get then. Okay, so in place of the u, again I put sine kt, which I have here. Then the v is e to the minus st over minus s. So this is my uv right here. Then minus integral of v du. The v is e to the minus st over minus s. So the minus s and this minus here will cancel. So the minus will be gone. And the du is here. It has a k in it. And in cosine kt dt. So I could pull the k out and I could pull the s out. It'd be plus here because again this minus sign cancel with that one. So it'd be k over s cosine of kt e to the minus st dt. Okay, we're going to apply integration of parts again to this guy here. But I'm out of space, so I'm going to erase this stuff over here and we'll keep going. Okay, so again we're applying integration of parts to this guy. So the u would be the cosine kt, dv be the same guy as it was over here again. I'm using u in both places here, I guess it's fine. So then u is cosine kt, so then du dt, derivative of cosine would be minus sine times derivative of kt. So it's going to be minus k sine kt using chain rule here. So then du would be minus k sine kt dt, and my v would be the same as it was in the first one. So the integral of dv is the same, so it's going to be e to the minus st over minus s. So plugging into the integration by parts formula, then here we get then, okay, so substituting in for u and v, and I'll let you check it's this then. We still have the k over s out in front here, so I can multiply it in. That would make this guy over here k squared over s squared. So let me do that right here. So multiplying this k over s in here, so doing that we get then, that guy changes to negative k squared over s squared. Now this whole thing we're going to substitute up here. So we're going to substitute this guy here. So let me do that substitution. I'm going to erase a few things and make that substitution. So doing that, we get then, okay, so after making the substitution up here, for the cosine guy, we get this. Alright, let me erase this bottom part here now, and we'll keep going. Okay, so notice we have the integral of sine kt e to the minus st here and here. So right here and over here. Okay, I want to take this integral of sine guy over here, so I'm going to add the both sides. And in front here, there's a 1 in front here. I can write that as, because I want to combine the fractions, let's write it as s squared over s squared. So in place of the 1 here, I'm going to write s squared over s squared. So I wrote this now as s squared over s squared here. Now I'm going to add this integral over to this side. So doing that, we get then, so adding the k squared over s squared integral part to this side, I can pull out the common integral part to have, and then add the s squared over s squared plus k squared over s squared. So it's going to become then s squared plus k squared over s squared, integral of the sine term. Then we still have these two terms here and here. Okay, now we're going to, now notice here we have the integral of sine kt e to the minus st, should be dt here. We have this guy, and that is the Laplacian up here. So let's make an observation. So the Laplacian is an improper integral because it goes to infinity as one of the limits up here. So we're going to write it as limit b goes to infinity 0 to b up here. And then I'm going to now write down here using the fundamental theorem calculus. Let me write the result here and I'll explain. Okay, so on this side, letting the limit go from 0 to b and letting b go to infinity, we'll just change the Laplacian of sine of kt here. And then here will be this guy, limit goes, b goes to infinity, evaluated at 0 and b. Okay, so I'm going to put b in place of t, then 0 in place of t, and work it out. Okay, I'm out of space here, so let me erase a few things and we'll keep going. Okay, so here's my guy up here. So I'm going to put b in place of t everywhere. Then subtract, put 0 in. That's what I've done here. So I put b in place of t here and here. I've actually brought the e to the minus st to the bottom and wrote it as e to the st and replaced the t with the b here. I'll explain why in a second. And also in this one I took the e to the minus st to the bottom, wrote it as e to the st, replaced the t with the b. Then over here, replacing t with the 0 will be sine 0 e to the 0 over s minus k over s squared cosine of 0 e to the 0. Okay, so now the sine of kb, b is going to infinity. Doesn't matter. The biggest the sine could be is 1. So it's basically sine goes between -1 and 1. It bounces around in there. Same with cosine. It goes between -1 and 1. So the sine and cosine are bounded between -1 and 1. But the e to the sb, that's going to go to infinity here. And let's assume that s is bigger than 0. So therefore, it's going to go to infinity on the bottom. So it'll be something. So some number between -1 and 1 divided by infinity. So it'd be 0 here. This will be 0 also. And the sine of 0 is 0, so this will be 0. And the cosine of 0 is 1 here. That's 1. So it looks like that's 0, that's 0, that's 0. That'll just be k over s squared, 2 minus signs. So looks like the whole thing will become k over s squared. Let's note that here. So the whole thing will just equal k over s squared. And now I can solve for the Laplacian of sine of kt by multiplying by a reciprocal here. Let's multiply both sides by a reciprocal of this. So doing that we get then. Okay, so multiplying both sides by the reciprocal of this guy, so it'll be s squared over s squared plus k squared. I'll solve for the Laplacian of sine kt. So multiplying this then by the reciprocal of that, of this here then, the s squareds cancel and become then k over s squared plus k squared. And that's what we're trying to show. So this proves property 1. So I'm not going to prove 2, but I'll let you go through and show if you want that Laplacian of cosine of kt will equal s over s squared plus k squared is proven in a similar way to this one. So it's going to use integration by parts twice in the same technique. Okay, so we're done with the theorem. So let's leave it there.